Hello and welcome back to this SlimDevOps Live episode 45. Today I'm joined by Primoz. Hello Primoz, welcome back.
Hello.
How are you?
Doing fine.
Good. So
Alright.
for those of you that are new here, Primoz works at Slim.AI in the engineering team. And if you're watching this after the fact on YouTube, this was originally streamed live on twitch.tv/SlimDevOps on, what is it today, the 26th of May 2002. So if you are watching this afterwards, please do head over to Twitch and give us a follow, and then you can join in these sessions live and join our communities, such as John, who's just dropped in. Hello there, John, and Takov, and Ranjan. I hope I've pronounced that correctly. But welcome back to all of you. If there's anyone else in chat, please, just say hello so we know who's here. So, this is a rerun of a webinar that I did give with CNCF yesterday. However, it was rather unfortunate. The CNCF's streaming provider had a rather significant problem, so it just streamed a blue box and my voice and nothing else, which was a bit disappointing given that I had a highly technical presentation that is also incredibly visual in nature. So we're running it again here for our community, and I'm hoping that the CNCF will be able to share this video around, and we're scheduled to do a rerun with them at some point in the future as well. So welcome back, Esme, as well. Hello there, how are you doing? So before we get into it, so Big Pod, it's been a while. It's been a crazy few weeks. What's new since I last spoke to you?
Well, I've been playing with what will soon be my website. That's something I've been trying to make in most insane way possible.
Does this mean you've been... Well, hang on a minute. If you say it's insane, I'm going to guess that you're not doing anything sensible, like using an existing sort of static page transformation platform. I'm going to say you have written your own static page compiler in .NET or C#.
Oh,
No?
No, I haven't gotten that far yet.
Okay.
I plan on doing something to that effect as well.
So what's your technique? What's crazy?
So first of all, I'm using their Blazor platform, which is basically C# in the browser using WebAssembly. So they compile .NET runtime into WebAssembly. So you're running actual C# in your browser. Then I'm using that as a skeleton of the website. Then I have sub-websites. Each of them have their own container, which is running as a serverless container in Azure Cloud. And then I have basically I have API somewhere else which has like article list and it statically generates the page where articles are shown and all that.
Okay.
And all like that. Yeah, I went partially to CMS, but I separated CMS from the actual website because I think backend for CMS should be somewhere else.
I agree. One of the places I worked at in the past, we used to use WordPress as the CMS, but we had a plugin which generated all of the content as static content. So we had WordPress, so all the marketers and what have you could have a nice way to create their articles, and then we just sent a static version of that content up to the website. Much better way of doing it. WordPress is notoriously vulnerable.
Yes.
Right, I see that Esme may have difficulties with her headphones, but thank you to those of you that have confirmed that the audio is in fact fine, and it's unfortunate that Esme's got busted headphones. Right, well, so since I last saw you, it's been crazy town round here at Slim.AI. 2 weeks ago was DockerCon.
Yes.
We had a big showing there, not least our Docker extension, which we're going to take a proper look at today because it's a very useful tool for what we're about to present today, and I'll get into that in just a moment. And then last week, I was in sunny Spain. and it was very sunny at KubeCon.
And I was in also sunny Slovenia, sitting right here, pretending I'm at KubeCon.
You were, and you did all of our virtual booth presentations and demos last week, right?
Yes.
Yeah.
Some
I tell you what,
better, some went worse.
It was a shame you couldn't make it because, as many of you will know, Slim.AI is 100% remote. As Big Pod's just pointed out, Primož, he's in Slovenia, I'm in the UK. I met colleagues last week that I've never met before. I've never met any of my colleagues until last week, and I met 5 of them last week. It was amazing. And they were from 2 from the USA, 1 from Amsterdam, 1 from Turkey, and 1 from India. So that was pretty fantastic. So it was a great event. We learned loads. We got lots of good feedback. And then I thought, you know what, I need to have a moment to, calm down and collect myself. After 2.5 years of sitting in this room, not doing very much, going to a major conference for 7 days was a bit of a shock to the system. So yeah, anyway, we got back, and like I say, yesterday we had a webinar with the CNCF, and that's what we're going to be presenting today. The topic is container complexity versus size versus security. So we've got, in fact, what I'll do is I'll share this in chat. I have written up all of this, so technically you can skip ahead. But everything that I'm going to cover is here, although Big Pod and I have been talking, and we've got some additional takes on some of this, so there's more for us to discuss than is covered in that article, and that article is going to be kind of a living document. We're going to add to it over time. But what we're looking at here is, how do you choose your base images for your containers, and what criteria should you be thinking about for your base images of your containers, and also the techniques that you use to create your containers, and had you considered security? And I suspect not in that last case, because we are going to show something very interesting today. Big Pod's got some additional analysis that he's been doing just a little bit earlier, which is going to supplement stuff that's not in that post. So I'm going to switch over to, oh gosh, it's been a while since I've done this. It's also unfamiliar. I'm going to switch down here. Oh, I've got a terminal window. That's interesting. So let's flip over to my browser. I'm doing this the wrong way already. Right. So this is the article that I've just shared. So let's just start by looking at this in order to understand what we're seeking to achieve here, so we're all on the same page. So the first thing is, and this is very important, container size is not a vanity metric. It's an indicator of container quality. So this is the sort of number one rule you need to keep in mind as we go through this today. We're really talking about image size being an indicator of container quality, and hopefully what you'll see by the end of this, that this statement is in fact true. So we're going to use the terms slim, minify and optimize interchangeably. And when we say either of those words, what we're talking about is the act of reducing the size of a container image. So here's why you should slim your container images. You should only be shipping into production what your app requires. Slim containers are faster to start because of the faster to deploy because of the lower size, and faster to start because of fewer files inside them. And slim container images can be less expensive to store and transfer as well. So slim containers also reduce your attack surface. Now this was something that we saw when Aisha put together her report, or Slim's report, but Aisha did all of the work on this. It's what we discovered when analysing the top 100 public container images. And one of the standout things for me was the increasing trend of dev, QA, test and infrastructure tooling being left in your production containers. And the reason that that's an issue is not necessarily because of the size impact that has, but if you do have an unfortunate bug in your own application and somebody exploits that and lands inside your now well instrumented container, they can use all of that tooling and those utilities to disrupt your operations in adjacent infrastructure. So slimming is important to actually remove that stuff so that if somebody does land inside one of your containers, it's a barren wasteland, and it's unfortunate they're in your container, but that's as far as they're going to go.
We should remember that those debug stuff, they're many times very, very instrumented. There are a lot of things you can hit, and sometimes even a lot of things that are connected to outside. So you can easily jump to a shell in your container, or sometimes even through that debugging system go outside the container and start messing with the host machine.
Yep, or those containers may well be in trusted IP ranges, which means that they can connect elsewhere, unauthenticated, or they have, like you say, curl or Kate's infrastructure tooling, and they can actually reconfigure your cluster on the fly. So it's all bad stuff. So it's not just about traditional, is the application secure? It's about worst case scenario, the application is compromised, you get an attacker inside a container, you don't want them to have a rich set of tooling available to disrupt your operations.
Well, in Kubernetes, as far as I remember, the container gets loaded up with authentication for the cluster. So all you need to do really, if you have direct access, is only to do is spooling kubectl, and you have at least partial control over the cluster.
Right. Yeah, indeed. So the objectives of our sort of live coding session today is that we're going to be using science to determine the best approach to containerize an application. I see Big Pod's just dropped off. That's fine. I will wait for him to reappear in the control room. So we're going to look for the best approach to containerize an application, and we're going to be focusing on these areas. Developer momentum, also you could call this developer experience. Low complexity, we're going to try and avoid having overly complex Docker files. In this case is what we're using to create these containers. We want to optimize for size, and we want to reduce the attack surface. And as we were just explaining, this is more than just the vulnerability count. We are going to do some vulnerability analysis, but as we were just explaining, this is about the tooling that's left inside the containers as well. So what are we going to be using to do all of this? We're going to be using ostensibly four things. The Slim.AI Docker desktop extension. That link will take you to the place where you can find out how to install that. That's currently in air quotes sideload, but by this time next week it will be in the Docker desktop extension marketplace. You'll get to see my Docker desktop in just a moment. You'll get to see how all of that works. We're going to be using Docker Slim, our open source project, to do the container minification optimization, and we're going to be using Sift to do some it will do full SBOM analysis. We've used it here many times in the past, but we're specifically going to be using this to do a package count analysis. And then today we've decided to use Trevi from Aqua Security, which is a security analysis tool. So those are the tools that we're going to be using. The Docker Slim, Sift and Trevi are all open source, and the Slim.AI Docker desktop extension is completely free to use. So you can reproduce these results. So how are we going to do this? We're going to first of all look at container construction. And here we have a very simple Python Flask application that implements an even simpler RESTful API. And what the app does is unimportant. It's purely for illustrative purposes, but we can have a look and see just how super simple this is. So here it is. It's Python and Flask, and we've got 2 endpoints. This is kind of irrelevant. The purpose is we're going to be looking at how the containers are actually built and the sizes of them and how to manage the sizes of them. But you've seen it. You can follow that through. And because we prepared this for the cloud native live, that was an app we created when we streamed with them previously. So that's a video to the previous thing we looked at. So we're going to look at the base images that we chose to use for this particular example. And BigPod and I have already got some ideas about how we could expand this. So if you've got ideas about other base images or techniques that we could be using here for comparison, please do submit those in chat, because we're definitely going to circle back to this and flesh this out with more examples. So the first container image, base image that we're going to be using is from the official Python images in Docker Hub. This is Python 3.9, their Slim image, so what they consider to be a minified image, and that's based on Debian 11, the Debian 11 code name being Bullseye. So that base image weighs in at 129 megabytes, and it comes with all the Python bits that we need. And then similarly, also from the official Python project, is their Python 3.9 Alpine image, based on Alpine 3.15, which is the current release. And again, that has all the Python bits that we need, and that weighs in at 58 megabytes. We're then going to use Ubuntu 20.04, which is the prior LTS, still supported. That's 73 megabytes, but there's no Python in there, so we're going to have to show you how we account for that. And then we're going to use the hot off the presses a month ago, Ubuntu 22.04. That's the current LTS. Again, no Python in there by default, and that's 78 megabytes. And then the other one we're going to use is a Distroless container, and this is going to be a multi-stage build. So if you've never seen a multi-stage build before, we're going to cover that as well. So those are the different base images to cover sort of some of the common ways that people are containerizing their applications. And, you know, we have already done a live stream that talks about why it is that Ubuntu 20.04 versus 22.04, there's a size difference. We actually did an on the day of release live stream on that. I'm not going to spoil that, but there's a video here Pete and I did where we dug into that. So the first thing I'm going to do is take a look at Dockerfile complexity, although I see that Takov has a question, so let's just cue that up. So Takov says, with Python, in my opinion, that's all the base image you would use. But honestly, the Debian Python official is the best in many ways to base upon. Yes, there are many good reasons why what you've said is true. A little spoiler, we come to a different conclusion. But if you go to the Python Speed website, they make the same recommendation, and we're going to cover off some of those points today as to why that would be the case. But we do come to a different conclusion today, so you know, pay attention. Right then, so first of all, we'll look at the Python container, and we started here because, as Takov says, this is a great place to start. So this adheres to best practice. We have, you know, pinned our Python version and the distro it's based on. We set our working directory, we copy in just the requirements file, we run our pip to install those packages. So in our layer construction, we'll have good progressive caching. You know, these steps shouldn't change very often unless we bump, you know, the version of Flask or whatever. And then we copy in the app, so that will create a new layer with just our app inside it. And then we define an unprivileged user, we expose the port, and we have a well-defined entry point. So this adheres to all the sort of core fundamentals of container best practice: good layer construction, unprivileged users, it's unpinned versions of things. So this is all good stuff, and this is a simple container image. It requires some knowledge of Debian or Ubuntu to know that this is a good unprivileged account to use for your app, but you know, there it is. That's that one. So it's definitely a great place to start. Now we're going to take a look at the Alpine image. So what changes here is now we're using Alpine as opposed to Debian as the base. We define the app directory again, so all of this is the same, but you'll notice there's no user defined here. So by default, Alpine doesn't have any user accounts. It's root context only. Now you can add additional steps to create unprivileged users and then use those users. I've not done this here for the purposes of simplicity and illustration. So we're just drawing a simple comparison here. We're not doing it. We could have done it. And I see we've got a new viewer. Hello there. I can't quite see. Is that one's Cal? I'm not sure if I'm pronouncing that, but welcome to the stream. Thanks for stopping by. And they say, let's just take a look here. They say Docker image tags are immutable. Not sure I would consider this pinning. Okay, so maybe pinning's the wrong semantics, but what we're doing here is we're expressing a version of Python and a version of the distro in all of these base images. And what that means is, instead of using Python latest, where you could suddenly get a new version, a new major version of Python suddenly turn up in your build pipeline, we're not going to get any unexpected changes like that. We are controlling the distro version and the language version in this way. So we're just avoiding those flag days when a new release is made, either of the distro component or the language component. Right then, so next we're going to take a look at the Ubuntu images. Now these are basically identical. I'm just gonna demonstrate this very quickly. We're just going to focus on the jammy images in terms of their content. The only thing that changes here is the version of Ubuntu. That's the only difference between the two, and this was what we used to dig into those differences between the major versions of Ubuntu a couple of weeks ago. So here, because there is no Python, what we're doing is we have this run statement here, which does all of the do your updates, install Python and all of its dependent components, then clean up after itself. So all of that happens in a single layer. And then exactly like the image the Docker file we saw with the Python Debian image, we set our working directory and our non-privileged user and all of that good stuff. So this is slightly more complex than the Debian image we looked at, because we have to install Python. And in fact, and so for me, somebody that's comfortable and familiar with Ubuntu, I don't consider this like a significant step up in complexity at all. So Big Pop, we've lost your camera. I guess you know that. Now, whilst we...
Yeah, better now than later when it runs out of battery.
And what we're going to do here is we're just going to look at a slightly different version. So the only thing that changes in these, you can see there's two. Oh, that's a lot of noise. There we go. There's these no rec versions, and basically all we're doing here is when we install the Python components, we're adding this line here to apt, which says don't install recommended packages, and that's so that we can better control the size of the image that we produce. So we'll look at the sizes of all of these in a minute, but that's the only changes between these no rec images. And then we have Distroless, which I hadn't done much with until quite recently. So when we look at this, the first thing is this is a multi-stage build. It's somewhat complex, and there were certainly some things you need to know about Distroless before you can tackle one of these. So you'll see that we're using that same official Python image based on Python 3.9 and Debian 11 as our build stage. And what we do in the build stage is we define a working directory, copy in our app assets, and then install the Python requirements. And that creates that part or that stage of the build. And then we use the Distroless container base image for Python 3. So this is, think of it as a Linux file system with just the Python interpreter and its standard libraries and modules. So none of the other things you expect to find in a container. So there's no additional libraries than is what is required by Python. No additional utilities other than what is required by Python. And this is the distroless nature of these images. And then what we do is we copy from our build stage our app, and then this is where we now need some knowledge about Python itself. And if we're developing a Python application, it's fair to assume we do have this knowledge. But we then copy in the site packages that were installed in the build stage into our what will be production container in order to provide the Python runtime that our app needs. And then just like the other images, we define our working directory, and we have to do this as well. We have to tell Python where those site packages are because of the way that Distroless works. So this is more complex. You have to understand how multi-stage builds work, and you have to have some insight into what is this Distroless container built from and what Python version does it have inside it. And we'll get back to that in just a little moment. I do see there's a few comments here. So let's have a look. So Paintface says, depends on the image registry you're using, I believe. Yes, okay. So so different registries can provide those tags in slightly different ways. You're dead right. And hello, Tommy Luco. Welcome to the stream. And then Takov asks a question. So let's see if we can bring that up on the screen here. So Takov says, so let's say we need external libraries from the build stage. Yes, so let's imagine we need libfoo. We would need to add another copy line in there that copies libfoo and any other libraries that our application absolutely requires, because the Distroless image is a file system with just Python. And so what we're doing is copying assets from the build stage into that blank canvas. And the sole purpose here is to keep the container image size down as much as possible. And
so
also
that's pretty complex and requires really good knowledge of our application.
Yeah, and we're going to find out later quite a lot of knowledge, in fact. Yes. And I couldn't do this without actually doing the step that we're about to do. So we're just going to go back and look at what we have here. So I've mentioned here that it requires knowledge of Python, the Python version of Python itself in order to create that production container. For example, what site packages, and as Takov points out, what additional libraries even we might require. And then it also requires knowledge of how the Distroless container is created, so that we use a compatible base image in the build stage. So let's just take a little look at that, because this was something, fortunately, I work at a company that makes tools for me to actually figure this out, because what is Distroless? What is it built upon? So we'll take a look. So this is Docker Desktop, and I've got the Slim.AI extension loaded here. And let's go and look at, I can't see it for looking, Distroless. Here it is. Let's take a look at the Distroless Python container. So we'll actually get that analyzing. So this is the file system But if we look at the overview, this was where the useful information lived. So it says base OS Distroless, and that's immediately disappointing because I was hoping to see something like Debian or Ubuntu or Alma or Alpine, you know, some recognizable thing, but it says Distroless. So what is it actually built upon? So let's go and look at some of the common places that would give us clues to that. So in Etsy, we should usually find OS release. Well, that's a symlink to userlib OS release. So we'll go and have a look at that in a moment. But we also have issue. So if we bring up issue and we look at the file contents, aha, here's our first clue. This Distroless image is built using Debian 11 Bullseye. So that explains why my build part here is using this container image. And many of you watching this may well be aware that Python 3.10 is available. Yet I am using Python 3.9. Well, why is that? So if we go back to our Docker desktop extension and we take a look in user bin, I can see that this is a Debian 11 based container with Python 3.9 in it. Now, before doing this little bit of exploration, I assumed Debian, I got that bit right, but I also assumed Python 3.10. And whilst I was copying all of the right bits into the right places, I had a container that didn't work. So this is one, you know, really nice use of the Slim.AI desktop extension. It's effectively a local version of our SaaS platform to inspect and diff and explore your container images. So I used the desktop extension here in order to understand the nature of this Distroless container so that I was able to do the right thing here and have the right Python versions here. That meant that this production container that was produced, all of the components were compatible with one another. So this is complex, I think. You know, it's a multi-stage build, and you have to do a bunch of research up front in order to figure out, have you got a compatible tool chain? So, and Ranjan also points out something else. Yes, because it's distroless, you're dead right. There is that the only account is root context. So like the Alpine image, we have no unprivileged user account by default. Now, again, we could have created one. I've elected not to, as a means to sort of illustrate the differences between these different techniques and approaches. So I see Big Pod's answering questions in the chat as well. So there are no stupid questions, Tommy. Can I bring that question up? Is that one you've already answered, Big Pod?
Yeah, that's one I already answered.
Okay, so if you want to field this question then.
Tommy asked that if there is an easy way to make Slim accessible in non-FHS compliant distros like NixOS. Basically, Slim should be available in any distro that allows installation of Docker.
Right.
So that could mean something like Fedora, which has problems with Docker, might not work. It depends on if you can get Docker working, or if Moby, which is what they use besides Podman, can completely fill that role in exactly the same way as Docker, which I believe it does, but I'm not sure.
Yeah, and also that's a great point, right? So we could try and add a Nixos-based image to our collection and try this out. Because like I said, I would like to build out these examples and comparisons.
And anything that is inside a container, any kind of container should work. So anything that any OCI compliant container, so that's anything kind of Docker, Podman, Kubernetes, all should run.
Yep. And just recently, Docker Slim has added support to operate inside of Kates, and we are going to be
still
adding...
in development and support.
It's not landed yet. Okay, it's in the pipeline, and on the roadmap is to add support for alternative container runtimes. So we just talked about, for example, Podman and also Containerd.
Yeah.
Right. Well, thanks for fielding that, and thanks for the questions. Right then, let's move back over here. So let's now take a look at container size. So I have pre-built all of these different containers with the exception of this one. So we're going to go through this, and we are going to build we're going to go through each of these examples with one container, but we do have all of them available.
You're using Microsoft Edge, and that
I am using Microsoft Edge.
That 3-dot menu that shows up when you select things.
Okay, I'm learning. Okay then, so let's head over to.
If you click on it, you can disable it.
So we're just going to build a container image. There's nothing clever about that. You've seen that before, I'm sure. So now what we'll do is take a look at this summary table. So we built all of these container images, and we used Docker Desktop to get the summary information. And as we've shown, you can do quite a lot with the Slim.AI extension. So here we have a clear win for Alpine, where the container image, which is Alpine base image, including Python and our application, weighs in at 62 megabytes. That's clearly head and shoulders above everything else, with our Distroless container coming in second place at 71 megabytes. And then we can see here, without any care and attention with our use of apt, the Ubuntu images are over 400 megabytes each. Now, this one here is built using the official Python Slim image, and that weighs in at 139 megabytes. Now, we didn't have to install Python because that was provided in that base image. But when we use Ubuntu and we add some additional apt know-how, not installing those recommended packages, we can actually get a container image that's smaller than this one here. So that's interesting. If the argument is this is the place to start, well, hang on a minute, I can get the same experience with Ubuntu and my container images are smaller. So let's just recap here. Alpine was a mega simple Docker file, and so was this one. But here's the rub. Alpine is great for Go and Rust, and there are other use cases that it's great for. But actually,
and even Python, at that, I'm not sure. Exactly.
Well, that's certainly something we should get into in another stream, I think, looking at Go and Rust particularly and the different options that are available there. And I do touch on this towards the end, and we'll circle back to that. But Python and Alpine are not good bedfellows. So, and this is also the case with some other languages as well with regard to Alpine, and that's because Alpine uses Muscle, which is an alternative libc implementation compared to glibc, which is in just about most Linux distributions. So some of the issues that can present is that your build times are considerably longer because the Python wheels, the way that pip installs packages that are pre-built, are not compatible with Alpine because they weren't built and linked against Muscle. So that C code has to be built, compiled manually. So that significantly blows out your build times on your containers. And the other issue is it can be slower execution anyway. And it can also introduce runtime compatibilities. Now, I've linked an article here to Python Speed, where they go into all of this in good detail. Now, the point I'm making here is that whilst the Docker file in our case works because our simple app is pure Python, doesn't require any compilation of C components. And
let's remember, many high-speed C components or many high-speed Python components are C. Yeah. That's how they get that high speed. Anything AI related, NumPy,
Pandas, NumPy, SciPy, they're all great examples of things that have C modules beneath them. So I will leave this as reading for the viewer to be aware of some of the issues that Alpine can present. So consequently, this is a complex platform to work with because it can introduce unexpected outcomes that do require a research effort and remediation on the part of developers. Whereas if you stick with Ubuntu or a Debian image and even a Distroless image, you are unlikely to encounter unexpected runtime issues and significant performance degradation or build time issues. So that is a consideration when working with Alpine. Know what the compatibility with Alpine is for your chosen language ecosystem. And then we talk a little bit here about using the Docker desktop extension. We demonstrated determining that Distroless was Debian 11 and Python 3.9, vital information we needed to be successful making a functioning multi-part container built on top of Distroless. Are there any questions that I've missed here? I see there's been a bit of chat. I think we're fine at the moment. Big Pod's fielding some of those. If I've missed anything, let me know, Big Pod, and I'll circle back to them. And then with regards to the Ubuntu image, the complexity here is you need to install Python. Now, the flip side of that is that Ubuntu is a very popular platform, well documented, well commented on in the community. So actually those steps to install Python, although I knew what they were, you can easily find by searching how to do it. So I think it's a wrinkle, but it's not complex. It's fairly easy to overcome. So we're very quickly going to do a little bit of package analysis here. So we're going to use Sift for that. Sift we've used many times before. I'm just going to show you what it looks like. It passes our container image, and it tells us that there are 116 packages that were found. And if we just output that, we can see that the report looks like this. So this is a manifest of every package. You can see those that were installed from Python and those that were installed through distro packages, and in this case that's Debs. So this is every package that is inside this container. So if we just flip back to here, here's a table of what this looks like. So we've obviously not rebuilt any container images here. We're just looking at what the package count looks like. And so this is interesting, right? We get down to Distroless here, which was, excuse me, oh, pardon me, which was, thank you, which was the second smallest container, but has the lowest package count. You'll notice that all of these are 11 for the Python packages, and that's expected because pip should be deterministic. So the same things should be happening for pip across all of these different build techniques. But the Distroless thing is interesting, right? Because if it's got fewer packages than any of the others, then there should be a correlation between fewer packages to a lower vulnerability count. Specifically when compared to like the Python 3.9 image, because we know that Distroless is based on Debian 11. So it should be have a better security stance than this one here, which has 3 times as many packages, and perhaps it should be more have a better vulnerability stance than the Ubuntu images that have got hundreds of packages. So let's find out. Let's do some vulnerability analysis. So we're going to use Trivy today. This is the other security scanners are available. There's obviously SNCC, which is exposed via Docker scan these days, or you can still download SNCC and use it that way. And also, what's the other one we use? Gripe. And I did need to use SNCC and Gripe. So we're going to run Trivy on this same container. It's updating its database of things, and it produces a report that looks like this. And so we can see that inside that container, if I scroll to the top, that's where the summary information for the distro packages, we can see there are 86 vulnerabilities in total, 66 of which are low, 3 are medium, 13 are high, and 4 are critical. So let's go and take a look at this. So let's just have a little look here, because I see that Takov is asking a question, which is this a fair comparison? When were the base images last built, updated, and packages updated? When these were built, they're using the latest versions of whatever is available. So it's fair in as much that they are all using the latest stuff for their relevant releases. So let's go and go back to the report here and look at the outcomes of this. Oops, I'm in the wrong. There we go. So the first thing to note is you can't deny that the Alpine results are excellent. There are zero vulnerabilities of any sort here. But Distroless, well, this is a little bit disappointing. So there are 46 in total, and 3 are critical, and 7 are high, and 4 are medium. And that's, you could argue, that is worse than this here. Or you could say it's better because, these are lower, but it's among the worst results. And that's curious because, let's remember these two, Distroless and Debian 11, are essentially based on the same fundamental components. But what's interesting is this. These Ubuntu results, even these big, fat, large ones, have 0 critical vulnerabilities. And this one here has 1 high. Now, this is interesting. We'll get to in just a moment, because that high there is actually a false positive. That is a security vulnerability that has been fixed, and you can read about it just here. And I did use gripe and snick on this container, and they both confirm that, this here is not a vulnerability that actually exists in that container image. So you have to sort of really ask yourself, what's going on here? Surely Ubuntu is derived from Debian. So why are we seeing this? And let's not forget, these versions here are 2 years old. The 2004, Ubuntu 2004 is 2 years old. Debian 11 is a year old. So how is this possible? So this is where we get into the discussion around choosing your base image. And the thing here is that Ubuntu is a commercially backed Linux distribution with a full-time security team that has SLAs to mitigate vulnerabilities for their customers. And those SLAs include mitigating all critical and high vulnerabilities for the supported lifetime of the distribution, as we can see in these results. Unlike Debian. So Debian is a community project, and while many Debian contributors, including myself, do fix security issues in Debian, it simply cannot provide the same commitment to security as the commercially backed Linux distro vendors such as Canonical, Red Hat, and SUSE. And had I had time, I would expect to see similar results in terms of the vulnerability counts in something like RHEL images, for example.
Not exactly.
Oh, okay.
I did some experimentation, some checking, and these are base images, so no Python is there. But for example, Red Hat's UBI, which is their universal base image based on Red Hat.
Okay.
And it has 100 vulnerabilities. They are all medium or lower, which means there are some, but they aren't the high vulnerability
Okay, so that looks like they must have a similar policy to Canonical then, to mitigate all critical and high vulnerabilities in their supported operating systems. Because as you can see, the medium and low count of these vulnerabilities in Ubuntu is pretty high. Now, admittedly, this has Python as well, but they're 104 and 140 respectively. So not so different from what you're telling me about the Red Hat UBI base image.
Fun fact, I also, for the base image of Debian 11, they also have a slimmed image and a big image. And vulnerability count is exactly the same.
Say that again.
Between Debian's slim image for Bullseye and their Bullseye image, so that's full fat image based on their server, vulnerability count is exactly the same. And exactly the same breakdown. So there was no vulnerability removed.
Interesting. And so you've looked at RHEL, and there are CentOS replacements these days. Did you look at any of them?
I looked at most of them.
Okay.
So I can just rescanning them just to see if it's happening. So, for example, if you just use the old CentOS image, which is CentOS 7, you get a lot of vulnerabilities. Many of them can be fixable just by update. So that is the important part, is that you should always update your image during the build process. There are some that say that you shouldn't, that it will produce at every time produce a different image, but well, better that than having your system exploited.
Yes, I need to write an article about this, because in this video that we scrolled over earlier, this one here, where we looked at 2004 versus 2204, I debunked that don't do updates, because I demonstrated that if you didn't do an update, you could clearly see there was a vulnerable package left behind, and if you did the update, you got the latest package from the security pocket and that vulnerability went away. So I absolutely subscribe to the notion that we should be doing updates as part of our build steps. I'm just going to change my earbuds, but carry on with your analysis of the other RHEL-based releases.
I also looked at Alma Linux and Rocky Linux. Alma Linux has 0 vulnerabilities found by Trivi, so I also use Trivi. And Rocky Linux has 4 vulnerabilities, but all 4 of them already have updates, so should be fixable just by update. I also looked at Fedora, which is community maintained, heavily community maintained, and it's also a lot faster than Red Hat and everything else. It has 0 vulnerabilities found by Trivi.
So that isn't unexpected from my point of view, because when did Fedora 30? This is 36, right? That came out 2 weeks ago.
Yeah.
And Fedora tends to lean into the bleeding edge, so all of its packages tend to be current. And certainly when we did that 2004 versus 2204 comparison, we did security analysis on those Ubuntu base images, and in exactly the same way, the Ubuntu 2204 base image right now has 0 vulnerabilities in it whatsoever. And the vulnerabilities that we see in these packages, in these base images, are as a result of installing Python and its dependent libraries.
I can tell you right now that Ubuntu Jammy has 20 medium vulnerabilities according to Trivi.
Oh, okay, you've just rescanned. So that's changed in 1 month.
On Docker Hub.
Yeah, so that's changed in 1 month, because
all of these images were were officially built by Docker, so they are from their library repository on Docker Hub. So if there is a build from the producer of the distro, you could have a different count, because they could be updating it a lot faster or even a lot slower. The exception to that is the UBI from Red Hat, which has its own, they control it themselves. It's not built by Docker.
So that base image has had a skew of 22 vulnerabilities in 1 month. Because like when we did that video, which was on the 24th of April, I think, or the 25th of April, that base image, fully up to date, had 0 vulnerabilities in it.
Yeah.
So it's remarkable how quickly things change. So hopefully we've explained that. Oh, hang on. Sorry, it wasn't Takov that asked that question. It was one's Cal. Sorry about that. But hopefully we've explained that adequately, and we've talked about the vulnerability assessment. So, and we've covered off where some false positives live and why the Ubuntu results outshine Debian. So let's get into a couple of what ifs here. What if I could have the low complexity of maintaining Ubuntu-based containers and the security profile of Alpine? And what if I can make my containers smaller than Alpine? So we're going to try that. So we're going to, I've given the game away there. Most of you have the link to this, of course, already. So let's just run this in our shell, and we're running here Docker Slim. We're running it against the same container that we've been using as our example container here all the way through. So this app doesn't require any additional tweaks or tuning to Docker Slim. It's exposed in such a way Docker Slim can walk it correctly. So there we go. Our minification is done. There's lots of information here, but we've broken this down into a table. So let's look at the container sizes. So here are the original full fat container sizes, and here are the slim container sizes. And what we can see here is that Alpine is now the smallest at 20 megabytes with just over a 3 times reduction. But what we can also see is that all of these container images are now within 6 megabytes of size of one another. So what's really interesting here is these large container images. This jammy container image here is 17 times smaller, and it's the same size as this no-rec. So did I even need to do this? Are these the same? Well, let's take a little look at that. So let's head back over here. We'll find our app, which is here. And we'll choose our, let's think about this. We'll choose our Vocal No-Rec Slim, which is the one without recommended packages, and we'll compare it with the Focal Slim, which was the larger image. So we won't click refresh there because it will restart this process. This is because I've just created that slim image. So here we are. We're looking here at these two images side by side, and it tells me that there are indeed some changes. Well, let's just flatten this and look at those side by side to figure out what they are. And it makes some sense. What they are is mostly Python bytecode. That is the difference between these. And also we see that there are some libraries that are pulled in differently. And this is because the way that Python works is it will DL load modules if they're available. So what we're seeing here is the difference between when those files were accessed and the bytecode being compiled and having different because it was derived from bytecode with a different sort of profile. You get a different bytecode output. It's never you will never get exactly the same hashes against bytecode when you've built that bytecode on 2 different instances of a machine at different times of the day. So what we're looking here is it's just the bytecode stuff, but everything else is the same. So what was the additions? They were symlinks to libraries, so doesn't actually add any size difference at all. And what else have we got here? The modifications, I think this is all bytecode. Oh, no, this one here. Oh, this is timestamps probably because they were built at different times. But we can say fairly accurately that these are effectively the same images. So there's an argument to be made that I didn't need to do these no-rec images, but I would say there is. Because if you want to keep the FAT containers as an artifact, having these smaller FAT containers is a good thing, right? So I would say actually using the no recommends, only pulling in absolutely the bare minimum is a good place to be, because you've then got smaller FAT containers to work with. But it just goes to show that Docker Slim will take, you know, your 400 and something megabyte container versus your 120 megabyte container down to ostensibly the exact same thing.
And
so
actually I would recommend keeping a big container as a artifact. At least that's, in my opinion, best practice.
I would, because you want to, it will be good to be able to have the two there for an A/B comparison to run your integration tests and make sure that both containers function in exactly the same way.
And even in debugging, it can help if you're going, why isn't this working? It might be actually a problem with your program, not with the Slim image, and that can skew your results of testing.
Yeah. So we used Docker Slim just now to do that minification. We could have used the Slim.AI platform. But the question is, did slimming the containers remove any vulnerabilities? So we're just going to take a look at this jammy no-rec slim image. Okay, so that's this one here. It's now 26 megabytes. And we're just going to look at this for illustrative purposes. So we already know that those Ubuntu container images don't have any critical or high vulnerabilities. So let's take a look at all of the medium vulnerabilities, of which there were 7, I think. And here they are laid out for us. So we can see that there's some stuff related to the extended file system utilities and its libraries. libsqlite, this again is extended 2 stuff, as is this, and then Perl. So this is the report from Trevi, and I've just annotated this slightly with what the search strings would be to actually find if these components exist in the Slim image. So we'll just go through a few of them. So we'll flip back over to Docker Slim. Docker Desktop with the Slim.AI extension. So our app is here. We're going, in fact, let's just get rid of this whilst we're here. We will load up the jammy no-rec Slim image, and we'll take a look at this. And then we'll go searching inside it. Now, what I'm going to do is do a flat search, and I think we can say E2F is the thing we want to look for, and that returns no results. So we know that all of the extended 2 file system utilities are absent from this container, meaning that all of these vulnerabilities are gone. Well, let's go and look and see if these libraries are available. So let's use not all of libcom. Let's be broad in our search, and I think the search I used was this. So libcom, let's go over here and do the same search. You get the idea of what we're doing here. We're inspecting our Slim container, and again, that library is not available, that component is not installed, those vulnerabilities don't exist. We can do the same for libext.
I have a question for you.
Sure thing.
Since you know this stuff better than me, why does a container need those libraries for ext4?
So a container doesn't. I mean, unless you attach a volume and you want to format a file system on an attached volume, it doesn't need those utilities, right? It doesn't need those utilities to mount that volume, because that's done outside of the scope of the container itself. Yeah. So, you know, they're there to provide I don't know if you remember this. If anyone remembers using Ubuntu from years ago, there was a project called Juice, JEOS, and it stood for Just Enough Operating System. And that was the proto version of the container and server image, these minimized container and server distributions for Ubuntu, which provide you just the bare essential raw ingredients to get something useful done. But you're dead right. If you're sticking an app inside a container, you don't need to operate it from the position of a human being. A lot of that stuff you don't require. And that's why Distroless exists. So I went down...
Slim exists.
Sorry, yeah, indeed. So I went down all of these and I searched for all of these things. And the conclusion I came to is all of the medium risk vulnerabilities have indeed been removed by using Slim.AI or Docker Slim when minifying the container image. Now, if you've been paying close attention, you might be thinking, why did we not use Trivy to redo the security analysis? And the reason is this. The minification process, also Docker Slim or Slim.AI, removes the package metadata. And that's what tools like Trivy, Gripe and Snyk use in order to assess what packages are installed and what vulnerabilities exist. So once you optimize a container, you can't use those tools. So what I'm doing in just a few moments is proving that these components are absent and therefore these vulnerabilities don't exist in my containers.
And that would be, and getting that kind of feature set, so you could check a Slim container is possible, but it is I actually looked at it how it could be done. It's basically you have to do by automated what Martin is doing right now by hand.
Yeah,
and you have to have everything essentially in a giant database. To what package every file belongs.
Indeed. So what we also discovered here is that removing SQLite also removed 2 low-risk vulnerabilities. So now we have our Slim container that it has 0 medium, high or critical vulnerabilities, and we've reduced the number of low vulnerabilities. But the question is, well, let's go and look at the low vulnerabilities themselves. So when I looked at that, there were several that were related to Python itself. Now that's interesting because we have a Python application. So let's go and look at what these vulnerabilities are relating to. And they're all relating to mail cap. So what we'll do is first of all validate that this is indeed a component that exists in the fat container. So let's go and do that very quickly. We'll flip back here. We'll switch our image over to the no-rec version. We'll analyze that. We'll switch it to a flat view because this is a nice way to look at this, and we'll look for anything mail cap. So this is in the fat image, and there they are. So what is this? This is the pure Python module, and here we have the bytecode that was compiled from that at runtime. So it exists in the fat container. So now let's go and look at our Slim container and do the same search. We'll flip it to the flat view. Mail cap. Oops, I've spelt that wrong. There we go. And we take a look in here, and indeed is nothing. And even though that mail cap is part of the standard library of Python, it isn't something our app required. So consequently, isn't in our minified container. And that means that all of these low-risk vulnerabilities that relate to Python itself are no longer in our container. Well, that's fantastic. We've now significantly reduced the attack surface of our container, and indeed what I was able to do is look at all of the remaining low-risk vulnerabilities. Here are all of their CVEs, and in just a couple of minutes I was able to use the exact same technique that you've just seen us using there, and was able to prove that in fact none of these vulnerable components exist in the optimized container, whatsoever. So what we have here is an Ubuntu container that has 0 vulnerabilities or 0 known vulnerabilities inside it. So the outcome of that is, yes, we can have our cake and eat it too. But what's interesting is this. There was a high-risk vulnerability, this is the CVE number here, that exists in glibc, which is present in, Ubuntu and Debian and most distros other than Alpine. And that has remained, that vulnerability exists in the Debian-based image that we were working on and in the Distroless containers, unlike Ubuntu, where it's already been mitigated, and unlike Alpine, where it never existed by virtue of Alpine using muscle. So even after minification, the Debian-based images do in fact still have high-risk vulnerabilities in those container images, and that's because those vulnerabilities have not been addressed. And that leads us on to some conclusions. So I'm going to start by saying I'm not going to suggest that you should never use Alpine or Distroless. If you're working with Go or Rust, then they are both good choices, and I would say particularly the Distroless static Debian 11 image, which is only 2 megabytes and is perfect for dropping in statically compiled modules, statically compiled binaries into, and I would prefer that over Alpine.
Well, but when you have fully statically compiled things, you can drop them into a scratch image, like with Go.
Yeah.
And then, so you don't even need a Debian image. You don't even need anything. You just need an empty
It largely is.
It's
basically a file system.
Yeah, that's what you need.
Not even a file system in this case. It's a directory hierarchy. It's Linux standard base hierarchy. With some minimal tooling, but again, maybe we should put something inside that image and see what we can do with Docker Slim. So to recap, what did we learn? Slimming container images is a vital process in the software supply chain story. You can reduce your attack surface, increase your deployment momentum, increase your startup performance, and make no changes to your existing container build processes. One thing we did find in all of this is that vulnerability scanners can produce false positives, and thankfully it's trivial to inspect container images to verify if vulnerable components are present. We've demonstrated that with the Slim.AI Docker desktop extension today, but that is obviously a capability that's derived from the Slim.AI SaaS platform. Alpine is indeed small and secure and has a low complexity Docker file. These are all good things. However, there are high complexity considerations with regards to language ecosystems and performance and compatibility impact when working with Alpine, and so that makes it quite a complex platform to work with, depending on the language that you're working with. And Debian is not the same as Ubuntu with regards to its security profile. So based on what we've presented here today, these are the outcomes. I would choose to use the jammy no-rec image Docker file. And I would even make a case for always using Ubuntu as a base image, regardless, because we've demonstrated we can get down to a 0 vulnerability, smaller than Alpine platform with Ubuntu. And we've got all of that ease of stuff. So let's look at some of this. I work in a team that's familiar with Ubuntu. So we can trade that slight increase in Docker file complexity, the bit where we had to install Python in a minimal fashion, and we gain a Docker file that adheres to best practice, a developer experience of using a familiar and well-documented platform, in this case Ubuntu, no runtime or build performance or compatibility considerations that can create friction, and a container image that is free of critical and high-risk vulnerabilities. So that's what we get before we even get to the optimization step. And if you add Slim.AI or Docker Slim into the CI/CD pipeline, we also gain a container image that is entirely free of known vulnerabilities, a container image that is three times smaller than the Alpine image, and just 6 megabytes larger than a slimmed Alpine image. We get faster container deployment velocity, faster startup performance, and perhaps this is a topic for another day. Docker Slim and Slim.AI can also automatically generate your AppArmor and SecComp profiles. So there's another security story we haven't even touched on here today, which we should probably dig into at some point in the future. So we started this whole presentation with the statement that container size is not a vanity metric. It's an indicator of container quality. So I say this: caring about container image size demonstrates that you care about the quality of the containers you deploy into production. Introducing slimming into your container production workflow can considerably reduce image complexity and attack surface whilst maintaining development velocity and adhering to best practice. So that's what we found today. I mean, I know that you've done some poking around in all of this. What do you think about those conclusions, Big Pod? Anything there you would counter?
I agree with most of it.
Okay.
But I would like to again reiterate, this is one of my favorite things to reiterate. Always, that as we're seeing with Debian compared to Ubuntu, just because it's open source doesn't mean it's secure.
Right.
That is something that is especially in Linux communities, fairly often told as a catch-all.
Yeah.
It's open source, it's secure. But that's not true. As we've seen, Debian is open source, but it's objectively less secure than Ubuntu by simple fact it has more vulnerable packages and higher vulnerabilities.
Yeah. And I think, the presentation we've done today has been useful because I want to think where we can go with this next. And I think your observations about the RHEL-based distros are valid. And, we should totally add some RHEL-derived distro base images to these comparisons to see how they stack up, because we can't deny RHEL-based distros are exceedingly popular. People are using them, and it would be good to know, how do those stack up. So I would like to throw in one or two of those, maybe SUSE and OpenSUSE for good measure. And
I didn't think of that in my research. Thanks for reminding
SUSE?
me.
Yeah. I have done a cursory security analysis of them in the past, and I tell you what, I'm not gonna say what I discovered. We'll save that for another stream. But the other thing I would like to add to this, which is the only sort of other exotic way of creating containers, would be to use build packs and see how a build pack container fares alongside the more traditional techniques. So that was that I think, over the coming weeks we should maybe add one a week to our portfolio of techniques and build out this doc, and maybe then do the same with Node and do the same with Rust and Golang, because I think the Rust and Golang story will be very different in terms of what we discover.
Yeah.
So, is there anything else you want to add to what we've discussed today?
Not really.
No, I think you make a good point, though. It's important to understand. And I think one of the questions we got earlier is, is this a fair comparison when the base images were last built and updated? So, again, that's something we should probably do something on, because the base images are updated frequently. Those Debian and Ubuntu base images, every time the packages are revved with a security fix, those containers get rebuilt. So even if you say Ubuntu :2004, that could be a different image that you're using tomorrow. The only difference being it may have new security fixes inside it, the major versions
or maybe
of
new
the packages.
vulnerabilities.
Well, indeed. I mean, that hasn't changed the image. What I'm saying is, as the distro vendors land security fixes in essential packages that are in the containers, they will automatically republish a revised version of that container image under the same tag. So just because you're using that tag over the lifetime of that container doesn't mean it's the exact same image every single day over that 5-year period. It is constantly receiving security updates. At least that's true for Ubuntu. It's true for RHEL. It will be interesting to do some kind of comparison with some of the other popular base images to see what their update frequency is. Well, we don't have any other questions, so I think perhaps we should put a bow on it there. But that's what we've got so far. You know where to find the doc. I will paste it in the chat. If anyone wants to add any additional feedback, ideas, or suggestions or observations on what we've presented here today, we'll gladly receive that and take a look at that and see how we can improve that analysis in the future. So, Big Pod, I think that's it for now. It's very late for you. It's quite late for me. I think we'll call it good there.
Sure.
Well, thanks very much for joining me. That was good. Next week we have Snick joining us. So we talked about Snick, one of the security assessment tools, and that is not just a security assessment tool. It's the security assessment tool which is now integrated into Docker. So we have a couple of members from the team from Snick to come and talk to us about what their tool does, and we will learn more together. So I hope you're able to join us for that. But for now, Primoz, thanks very much for joining today. Thank you very much for your questions and comments, and we will see you all soon.
See you next time.
Bye for now.